now we will see about electricity, okay, which is one of the important topic for competitive exams. Electricity here, mainly important one is about charge, represent with Q. Okay. If you see the properties of the charge here, charge actually it is the property of the body which exists as dual in nature. Okay. Charge exists as dual in nature, which is of we are having a positive charge is there and a negative charge is there, okay, plus Q and minus Q. And as we are having two charges are there, positive and negative, as their nature is different, here the force of attraction or the interaction between them is also in two different ways we have. One is charges, unlike charges actually attract each other, and like charges repel each other. Okay. Like charges attract and unlike charges repel each other. Okay. As the like charges are attracting, unlike charges are repelling here. Okay. Now the charge we are taking for the case of electron, which is having a negative nature we are having, of which one electron charge it is equal to 1.6 into 10 power minus 19 coulombs, where coulombs is the unit of charge. Okay. Coulomb is the unit of the charge here. One electron charge is equal to 1.6 into 10 power minus 19 coulombs, that is. Whereas if you are taking a proton which is taken as a positive charge, that is plus, that is having same magnitude is same, which is of 1.6 into 10 power minus 19 coulombs. This is having a negative nature and this is having a positive nature, means plus Q and like minus Q, that is. Okay. So unlike charges attract each other and like charges repel each other, that is. Okay. Now if you are taking these charges, if it is passing through any of the conductor here, means conductors are nothing but which allow the charges to flow through them. Okay. The charges, the bodies or the substances or the materials which are allowing the charges to pass through them, those are called as electric conductors, that is. If it is not allowing to pass through them, those are called as electric insulators, that is. So conductors means best example for that we can take silver, copper, like that we can take. And best insulator if you are taking wood you can take, rubber you can take, any other. Okay. So these are called insulators, and copper like silver we are taking that as conductors, that is. Now in this case of this electricity part, now we are discussing about the conductors here. How the conductor is allowing the current to pass through them and what is this current means. Okay. Now see, as charge is present here, if the charge is flowing through any of the conductor, the rate of flow of charge, that only we call that as current. So current means which is represent with I, the rate of flow of charge is called as current. Whenever these charges, if it is flowing through a conducting wire there in the given time, that only we call that as current. So of which current I is equal to, formula is Q by T, that is. Whereas Q means it is of coulombs and time it is of seconds. So I it is of coulomb per second, that only call that as ampere. Means if 1 coulomb of charge passes in 1 second, then the current drawn there is equal to 1 ampere current. Very important one. See that again. So current I is equal to Q by T means if you are taking the charge you are taking which is passing through the conductor is about 1 coulomb is there, then the time taken there to pass through that conductor, if it is of 1 second, if the charges are flowing, then the current drawn in that conductor or in that circuit, we call that as 1 ampere current, that is. Okay. That is called as ampere. That is the SI unit of the current here. Now you see how these conductors are allowing the current to pass through them. Actually any of the metal conductor if you are taking, we are already having free electrons are present inside that conductor there. Say for example, if you are assuming a wire, a cylindrical line, like this. Inside this wire, the electrons which are present, which are of free ions are there. Those free ions actually they are moving in different directions like this. As it is a metal, the charges are moving in different directions, that is like this. Okay? Whenever if the charges are moving in different directions, the net charge which is passing here is becoming 0. So, which means there is no current is drawn in the circuit or not drawn in the conductor, that is. Okay? So, if the charges are going in different directions, the number of charges passing to left side is equal to number of charges moving on the right side. Finally, the rate becomes 0 here. So, that is why here whenever if you are touching any of the conducting wire there, okay, there is no electric shock. But once if you are connecting this one to a battery, then what happens there is, for suppose if this wire, if it is connected to a battery like this, then what happens there is, here there is a change in the direction of these electrons, of which now all are going in one particular direction here. It becomes like this. All are going in one particular direction. Like this. See, the difference to this one and this one is, when there is no battery is connected, the direction of motion of the charges are in random motion, they are going in different directions. So, that is why the net flow of charge is becoming 0. But once if you are connecting a battery, that battery is making the charges to move in one particular direction, that is. Okay? So, that as the charges are going in one particular direction, what happens there is, we are having a rate of flow of charges present. That rate of flow of charge only we call that as current, that only called as electric current. This is given by Lorentz and Drude theory, that is, who gave that? Lorentz and Drude, two scientists. This is called Lorentz and Drude theory. Okay. So, which means whenever there is no connection of battery is there, the charges are moving in different directions, random motion we have, but once they are connected to a battery there, what happens there is the charges are moving in one particular direction. As they are going in one particular direction, we are having a rate of flow of charge comes, and that rate of flow of charge only we call that as electric current, that is. Then how this battery makes the charges to flow in one particular direction, that we will see now. How the battery is making these electrons which are going in a different directions, okay, how it is making these electrons to move in a one particular direction, that we will see now. Okay. See, whenever there is no battery connection is given, as we know that they are going in a different directions, but once you are connecting a battery to that battery inside, we are having a force called electromotive force is there. Okay. A force is making those electrons to move in one particular directions, means this battery is doing some work on these charges to go in a one particular direction, that is. Okay. So, which means as it is doing the work done, W is equal to F into S. Here F is the force of which driving those electrons to go in one particular direction. Let it be that force is electric force, Fe, that is. Okay. And here the displacement is nothing but the length of the conductor we are taking here. So, which means as W is equal to Fe into L, that is. This is the work done by the battery on the electrons, so that they can go in one particular direction to get the electric current. Now, here in this case, on every charge, on the unit charge, how much is the work it is doing, that battery is doing, that only we call that as its potential or potential difference, or it is also called as voltage, potential difference. Okay. Potential difference V is equal to whatever the work done by the battery on the charge or unit charge, that only we call that as potential difference. As V is equal to W by Q, then W we already know that is of F into S, we are taking that as Fe into L, that is. Then V becomes V is equal to Fe into L by Q, that is. Okay. So, voltage V is equal to W by Q, that is its formula. So, as this battery is doing some work on the electrons which are going in different directions, now due to this work done, they are going in one particular direction which is causing the current. So, which means that we are having a relation to the voltage and to the current here, because of doing the work done on the unit charge only, as they are going in one particular direction, we are getting the current. Current is drawn in the circuit, or current is passing through the conductor here. Okay, and that relation only later we call that as Ohm's law, that is. Okay, that only called as Ohm's law, that is. As V is equal to W by Q, then its units we can write that as W it is of joules and charge it is of coulomb, joule per coulomb, that is. So, voltage or potential difference, it is also called potential difference. It is nothing but the work done by the battery on the charge to move inside the conducting wire in a particular direction, that only we call that as voltage or potential difference. Okay, have understood now? The work done on the unit charge done by the battery to move in one particular direction in the conductor when connected to a battery, that only we call that as potential difference or voltage. Okay, and its units in SA system if you are taking, as it is of joule per coulomb work by charge, which is of joule per coulomb, that joule per coulomb only we call that as volt. Okay, voltage as volt. Volt is the unit of the voltage here, and that volt, 1 volt is nothing but equal to 1 joule per coulomb. And what do you mean by that 1 joule per coulomb means? Here we are taking, if you are doing a work of 1 joule on 1 coulomb of charge, then the potential difference maintained there is 1 volt. The potential difference there is 1 volt, or you can write like this also. The work done required to move a charge, okay, of 1 coulomb is how much, that is 1 joule of work is done there. So that the potential difference it is maintained is nothing but equal to 1 volt, that is the unit. Okay. So 1 volt is equal to 1 joule per coulomb. As because of due to this doing work there, the voltage difference or the potential difference is present, there is a production of current is there, current is generating there, current is coming there. So that's why depending on the voltage you are taking, the current varies. That only we call that as Ohm's law. Very, very important one. Okay, which is called Ohm's law, that is. Now we are seeing this Ohm's law. According to this Ohm's law, here whatever the potential difference or whatever the work you are doing on the unit charge there to go in one particular direction, depending on the work done only, means indirectly depending on the voltage only, we are having the current is coming, which means at a constant temperature, because if the temperature changes, very, very important thing, at constant temperature only we can apply this Ohm's law. The temperature should remain same. If the temperature is more, then the random motion of the electrons is also more. If the electrons are going in different directions with more speeds, it is very difficult for the battery to keep them to go in one particular direction, means resistance is increasing there. So that's why to apply this Ohm's law, we have to consider at constant temperature. At a constant temperature, whatever the potential difference we are applying, V, okay, means the work done on the unit charge, whatever the potential difference we are applying, V, is directly proportional to the current drawn. Directly proportional to the current drawn here. Means here depending on the voltage we are getting the current. So means more voltage, more current, less voltage, that is. So means here I want to get more current, then the voltage I have to apply there is more. Like we see in case of our batteries, 2 volts battery, 3 volts battery, 4 volts battery, like that. That voltage represents whatever the work it is doing on the charge to move in one particular direction. So means the current, electric current, the current I, actually it depends on the voltage, is depending on voltage which is of V. As I is directly proportional to V, means more voltage, more current, less voltage, less current only we drawn. Then as V is directly proportional to I, then I is equal to a constant K into V. That constant only we are taking that as 1 by R. That is called as 1 by R, which is called conductivity. Later we will see. Okay. So this is the form, of which we can write this one as V is equal to, if you bring this R this side, then V is equal to IR. This is the mathematical form of Ohm's law, that is V is equal to IR. See the statement again, at a constant temperature, whatever the current you drawn is directly proportional to the voltage or the potential difference we applied, because that potential difference is nothing but whatever the work it is doing on each charge to go these charges in a particular direction. If the charges are going in one particular direction, we are getting the current. That current depending on the voltage we are taking that. So that's why as I is directly proportional to V, then I is equal to a constant K into V, then I is equal to V by R, that is. Okay. Or you can write that as V is equal to IR, where V is the voltage, we already know that, and I is the current. Now we got a new physical quantity, we call that as resistance, that is. Okay. So in V is equal to IR, V is the voltage or the potential difference, I is the current drawn in the circuit or in that conductor passing there, and R is the resistance offered. Now we got a new physical quantity which is called resistance. What is this resistance? Resistance means opposing or stopping. Whenever, if you are considering any of the conductor, as these electrons are going in different directions, so that whenever it is connected to any of the battery, as they are going in a particular direction here, whenever these electrons or these charges are moving in one particular direction, here there are positive charges are present, of which we call that as protons. These protons try to attract the moving electrons here, so that as they are attracted towards these protons, some of the electrons getting stopped here or they are slowing down. That only we call that as resistance. And those positive charges or those protons, their structure, that only we call that as lattice. That only called as lattice. The arrangement of positive charges present inside the conductor, that we call that as lattice. Okay. For example, if you are taking a conducting wire like this, now here the electrons are moving in one particular direction, one of the electron is passing here. I have a lattice structure like this. Whenever these electron is moving here, that is attracted towards this positive, so that that electron which is having negative charge, as it is attracted towards the positive charge, because both are unlike charges attract each other, the electron velocity gradually decreases there. And so that whenever it crosses the first proton there, next again one more positive is there, and again it is attracted towards that one. Again there is a decrease in the speed, and whenever it passes there, again one more positive we have, and again it is attracted towards that, and again there is a decrease in the velocity is there. So that finally what happens there is some of the electrons, some of the free moving ions, they are getting stopped inside that conductor, and depending on the work done by the battery, the electrons are moving here. Okay. Actually, with the velocity with which those electrons are moving in one particular direction, that velocity only we call that as drift velocity. That is called as drift velocity. Actually, if you take the drift velocity it is about 0.07 millimeter per second. That is the velocity with which the electrons are moving inside that conductor. Okay, it is moving inside that conductor there. Then if with the velocity of 0.07 millimeter per second means very less velocity, that is, then how it is possible whenever if you on a switch, immediately we are getting the reaction there, like fan rotating or the bulb, here in very less time we are getting that reaction there. How that is possible is, current passing means rate of flow of charge. There is no relation to the velocity to that one, because every electron movement in the per second there, that gives you the strength of the current. So, depending on the strength of the current, we are having that reaction is coming. And this is about the velocity of the group of those electrons which are moving in one particular direction. That average speed is 0.07 millimeter per second, that is. Okay. So, from this Ohm's law finally we got as V is equal to IR, where R is the resistance. That resistance offered is because of due to the lattice structure, because of due to the positive charges present inside the conductor there. This you call that as resistance. Okay. Now, this resistance actually it depends on some of the physical quantities here. That factors which are affected by this resistance, now we will see. So, Ohm's law statement what? Always remember, at constant temperature only we can apply this Ohm's law, that is, of which the electric current drawn is directly proportional to the potential difference we applied. Okay. So, I is directly proportional to V, that is. Okay. And another important limitation of this Ohm's law is, this Ohm's law is valid only for the case of these conductors, very good conductors like copper you can take, like iron you can take, like silver you can take, like this metals are cases only. This is not applicable for the case of gaseous state here, and whenever there is a change of temperature is there, we cannot apply this one. Okay. So, until that constant temperature you are taking for the case of the metals, now we are having, if you draw a graph between the voltage and the current there, here we are getting a straight line which is passing through the origin. If the voltage is increasing, then the current also always increases, that is. Okay. V is directly proportional to I. This is for only for the case of ohmic conductors, that is. Means which are following the Ohm's law. For that case only we are having these ohmic conductors. Only for these ohmic conductors only we are having a graph like this. Whereas if you come to the case of any other conductors which are non-ohmic, particularly like gaseous conductors, if you are taking, the graph is no more like a straight line. Here we are getting a curve. Like this, here we are getting a curve. This is for non-ohmic conductors, that is. This is for non-ohmic conductors. Okay. So, we cannot apply the Ohm's law for the case of non-ohmic conductors like gaseous conductors you can take, or LEDs you can take, or even for the case of semiconductor devices like silicon, germanium. For these also we cannot apply this Ohm's law. Okay. For them we are getting a curve. It is no more like directly proportional here. I is not directly proportional to V in those cases. So, limitations are what? It depends always on the constant temperature you are taking, and it is applicable only for the case of these ohmic conductors and not possible for non-ohmic conductors like gaseous states there, gaseous conductors there, and another one is LEDs we cannot apply to them, and not only that we cannot apply for the, even for the case of these semiconductor devices there, semiconductor materials there. Okay. That is about Ohm's law and its limitations, that is. Now, we will see on what factors does this resistance of a conductor depends. Okay. Now, we are seeing the resistance and its factors. Factors affected by resistance. Factors affected by resistance or resistor. Resistance of a resistor, that is. Okay. The first important one is about the length. Whatever the resistance it offered by the conducting wire, it is directly proportional to the length you are taking, or is directly proportional to the L, where L means the length of the wire. That is called the length of the wire. Because when you are increasing the length here, then what happens there is, as more positive charges are present, means in the lattice structure we are having more positives are present. Whenever the electrons are moving here inside the wire, okay, whenever the electrons are moving there inside the wire, so more chances of obstructing that. Whenever you are increasing more and more the length there, gradually the speed of the electrons decreases and gradually there is no current is there, means the resistance is gradually increasing. Okay? So, that is why the resistance of a wire or a conductor, it is directly proportional to the length of the wire you are taking. As more resistance is there, then the passage of current is less in those cases. That is why whenever if you see any of the electronic appliances connections here, from the switch at most least distance we are taking for the conducting wire there. That is because of due to if the length of the wire increases, then the resistance offered by the wire also increases. So, that is why we need very less distance, particularly in case of AC power switches, we will see that one. Okay? And another factor we are having, that resistance is inversely proportional to the area of cross section, which is about the thickness of the wire. Area of cross section means whenever if you are having more and more thickness is there for the wire, then more number of free electrons are available there. For example, like this, if this is the thickness of the wire here we are having more number of electrons are there, and at the same time more positive ions also present there, more lattice also present there, positive ions are there. But still, as we are having more number of negative charges are present, then what happens there is more number of electrons are having a chance to pass over the ions there, positive ions there, through the lattice structure there. So, that is why here in this case we are getting more amount of current, means the resistance is gradually decreasing when you are increasing the thickness of the wire. So, more thick wire and more current is passing, and if the thin wire if you are taking, less current only passing in that. And at the same time if you take the resistance, for if you are having more thickness, the resistance is less. If you are taking a thin wire, the resistance is more we have. So, it depends on the thickness of the wire, thickness. Okay? And if you combine both the statements 1 and 2, now we are getting R is directly proportional to L by A, that is. Then R is equal to a constant K into L by A, that only we call that as resistivity, which is represented with rho. Okay? Which is called rho. So, here R means resistance, whereas L means length of the wire or our conductor, A is the thickness or area of cross section, and rho is nothing but resistivity. Resistivity. Okay? Rho is called resistivity. More and more resistivity we have and more resistance we have. So, resistivity actually depends on the nature of the substance we are taking or the nature of the material of the conductor you are taking. If you compare to the copper and silver, both are conductors only, but still silver resistivity value is less, whereas for the copper the resistive value is a bit more we have. So, that is why silver conducts current very easily when compared to the copper, because the resistance level is less in case of this silver, whereas it is a bit more in case of this copper. Whenever the resistivity value is becoming infinite, where we are having the resistance is infinite, those only we call that as insulators. Those only we call that as insulators, that is, which are not allowing the current to pass through them. Those we call that as insulators. For them the resistance is infinite we have. Okay. Now we got a new physical quantity which is called resistivity, rho, that is. Okay. It is called as resistivity, rho. As we got R is equal to rho L by A, then from this you can write R into A is equal to rho into L, then rho is equal to RA by L, that is RA by L. This is the formula for resistivity. Okay. And if you are taking that R is equal to, so rho equal to RA by L, if you are taking area of cross section is 1 meter square and the length also if you are taking as 1 meter, then rho is equal to resistivity is nothing but equal to the resistance. So, resistivity means the resistance offered by 1 meter of wire having thickness 1 meter square, that only we call that as resistivity. That is called as resistivity that is. Then it comes to the case of units. As R we are having the units, R is equal to, it is of V by I, where V is the voltage volt by I it is of current that is, which is of ampere that is. So volt per ampere, R is equal to V by A, volt per ampere, its units. That volt per ampere we call that as ohm, or with a symbol like this. Okay, ohm that is. So that is the unit of resistance. Now if you are taking for the case of this resistivity the units there, so we know that rho is equal to RA by L, then R it is of ohms we have, and area it is of meter square, and length it is of meters. Then resistant units is, resistivity units are ohm meter, that is called as ohm meter. That is about the resistivity of any of the material. Now if you are having a resistivity is there, then the reciprocal of the resistivity only we call that as conductivity, that only called as conductivity that is. So means the reciprocal of resistivity we are taking. Next one, conductivity, which is represented with sigma. Then conductivity sigma is equal to 1 by rho that is. 1 by rho means that is of reciprocal of resistivity that is. So we know that rho is equal to RA by L. Then sigma is equal to L by R into A that is. This is the formula. Okay. So as rho is equal to RA by L, if you substitute that, rho is equal to L by RA we got. And what about the units of conductivity? Units it becomes resistivity there, then we will get 1 by ohm meter that is. So means you can also write that as ohm inverse and meter inverse, or you can also write that as MHO, mho that is, reciprocal of ohm. Okay, mho that is, ohm inverse, meter inverse, or 1 by ohm meter that is. That is about conductivity. Conductivity is about how much is the capacity that conductor is having to flow the charges through them, that only we call that as conductivity that is. Okay. So conductivity and resistivity both are inversely proportional to each other. As the insulator, if you are taking an ideal insulator there, then its resistivity value is infinite. And if you are taking for the case of an ideal conductor, then the resistivity value becomes, that conductivity value becomes infinite, so that the resistivity is becoming 0. And in the same way, if the resistance, if you are taking that as infinite for a ideal resistor there, then its conductivity 1 by infinite, that is becoming 0 that is. That is about the conductivity and resistivity of the given conducting wire. Okay. Now we will see as about the resistance. We already seen that on increasing the length, the resistance is increasing here. Now we are seeing if these resistance or resistors, or if you are considering, if you are taking those resistors in a series connection or a parallel connection, very important one. Now we are seeing if suppose the resistance is which is connected, the resistors which are connected in series we are taking. Okay. So actually the symbol for resistance is like this. This is the symbol for resistance. Now these resistance we are joining them one after another. Okay, one after another here means like increasing the length. If the length increases, the resistance also increases. That we will see now. Let us suppose if I am having a resistor R1 with resistance there, and another resistor with resistance R2, and third one we have having the resistance there R3. Now all are connected to a battery here like this. Now if you observe, if you are connecting the battery there, of which the current is flowing here inside, let us suppose if I is the current passes. If the current I is passing, now the current I, first it passes through R1, next it passes to R2, next it passes through R3. And we are taking the resistance with the different values we are taking, R1, R2, R3, all are three different one we are taking. So that what happens there is, as the same current passes through R1, same current passes through R2, same current through R3, the potential difference required there is different because the resistance is not same. For example, if you took R1 is less than R2 less than R3 if you are taking. Means the resistance offered by the first one is less, then we need not to do more work for the charges to move through that one. Okay, less for the case of battery here to work on that particular resistance there. So that's why here the voltage value is different. And when came to the case of resistance R2, it is a bit more than R1. Means the work done by on the unit charge by the battery it is more in case of R2. Means here the potential required there is different. And when come to the third case R3, it is more we have. So that's why here what happens there is, as more resistance is present, we have to do more work there, so that we can move the charge through that, so that we can get the current passing through that one. So that's why as the resistance for the third one is more, the voltage at that point is also required, there is more we have. So that's why let us suppose the potential drop at here in the first case of resistance is V1, second case let it be V2, and third case let it be that is V3 if you are taking. Then throughout all the three resistance, the current passing is the same, is the same current I only passing. Okay. Then all that total voltage V1, V2, V3, that potential drop, it is coming from V let it be. Okay. So means this potential difference V is distributed at R1 as V1, at R2 as V2, and R3 as V3 that is. Then we got V is equal to V1 plus V2 plus V3. Okay. And we also know that the current remains the same in all the cases. So means I is equal to constant, which is I1, I2, I3, which is the current passing through the resistance there. All the three cases it is the same. Let it be that is I. Now, when come to the case of resistance, as the resistance we are having a different is there, then if you substitute that V is equal to V1 plus V2 plus V3, and we know that according to Ohm's law, from Ohm's law, as V is equal to IR, then I into R is equal to, where this R is the equivalent resistance we are taking that. Okay. So means the combination of all the three resistance we are taking, the equivalent resistance when connected in series is equal to IR equal to V1 means I1 R1, V2 I2 R2 plus V3 I3 R3 that is. So which means I of R EQ, equivalent resistance when connected in series, is equal to I1 equal to I, I2 also equal to I, and I3 also equal to I. Then if you take common that I, then I or S is equal to I of R1 plus R2 plus R3 that is. That I get cancelled. And we are having the resistance offered in the series there when connection in series. All the resistance are added directly, of which we are getting R1 plus R2 plus R3. This is the case. RS is equal to R1 plus R2 plus R3 that is the final resistance we got. What do you mean by this is, if you are having three resistors of R1, R2 and R3 is present, then directly you can take in place of those three resistance. This is equivalent to, we can also write like this. We are using one big resistance there and the battery there given. Okay, so that this resistance we are taking that RS value here, RS, like this. This is its meaning. Okay, so whatever the resistance you are taking, all that in series R1 plus R2 plus R3, all that we are taking that as one resistance, that is, which is of RS. That only the equivalent resistance when the resistors are connected in parallel. And if you observe, as RS is equal to R1 plus R2 plus R3, so means that final resistance we are getting is always more than the given one. Okay, as we are taking the algebraic sum here. That is about when the resistance are connected in series connection, that is. Then if you see in the same way for the case of parallel connection, if you are taking here, parallel connection means the resistance you are taking not one after another, one on another we are taking that. Okay, like building the blocks. Okay, now see like this. Here we are taking a battery and now we are taking one of the resistance. second resistance, third one here like this. Okay. Now, as three resistors are there, R1, R2 and R3. Just like the previous case, we are taking R1 less than, R2 less than, R3. Means the resistance offered by the third one is more, whereas R1 is less and R2 is in between R1 and R3, that is. Now, as this battery voltage is directly connected for the resistance R1 and directly connected to R2 and directly connected to the R3, means in all the three cases we are having the same voltage is present. So, which means whenever if a parallel circuit is given, if the resistance are connected in parallel, whatever the voltage we have connected to the battery, the same potential difference is maintained throughout that resistance. Okay. So, that is why here the potential difference at R1 is V, R2 also V, R3 also V here. Okay. Same voltage only present there. But whenever if you are taking the current as is started here, now here we are having two different paths are there for the current. Let it be here I1 it comes and remaining current is going up to, and next let it be this is I2 and let it be this is I3 like this. As I2 is dividing there, let us suppose if I is the current passing, then I1 comes this side, then upward going is I minus I1. Then next going I3, that is nothing but I minus I1 minus I2. That current is passing through I3. Now again I3 is coming and joining here with I2 and I2 again joining here. Finally again we are getting the back the current there, I, like this. This is the circuit now. Okay. Now as all the resistors are present here in parallel, as the voltage is the same, but the potential, the current here passing is different, because here if you are taking the case of R3, okay, the resistance offered is more, but the same work done only we are doing that. If the work done is same, but the resistance is more, then the current passing through that is less, means I3 value is less. That is why you wrote I minus I1 minus I2. Okay. As the resistance offered by the first one R1 is less, means as the same work done we are doing, even the resistance is less. That is why the current passing through that resistance 1 is more. So, that is why here we are having for the case of current 1 there, only I minus I1 only passing through that one. Okay, like this. So, the resistance more, we are having current is less. As the resistance is less, the current passing through that is more we are having. So, that is why in this case, as the voltage remains the same, I am taking V1 is equal to V2 equal to V3, all the cases that is taken as V only. Whereas in case of the current here, the current it is dividing, the total current I, it is divided as I1, I2 and I3, that is. Okay, I1 plus I2 plus I3, that is. And we know that as the resistance is different here, and we know as V is equal to IR, okay, as V is equal to IR, then I is equal to V by R, that is. Okay. Then if you substitute that here, the complete total current if you are taking with the complete voltage there, then it is of V by the resistance which is offered when it is in parallel is equal to I1 which is of V1 by R1 and I2 which is V2 by R2 and I3 which is V3 by R3, that is. Okay. And we know that in all cases the voltage difference V1 equal to V2 equal to V3, that is. Then V by Rp is equal to V1 is V, V2 is V and V3 also V there. Then 1 by R2 plus 1 by R3 and R3 is there. Then if you take common, then V by resistance in parallel is equal to V of 1 by R1, 1 by R2 plus 1 by R3, that is like this. Then we get cancelled and finally we got resistance and the parallel circuit, it becomes 1 by R1, 1 by R2 plus 1 by R3 like this. Okay. So, means as we are getting all are in reciprocals are there, then what happens there is here we are having that R1, 1 by R1, 1 by R2, 1 by R3, then the resistance offered, if you are connecting all that in parallel, the resistance is becoming less and less because we are taking the sum as reciprocal here. Okay, so that's why we are getting very less resistance here. Whatever the resistance we are getting when connected in parallel, when compared even to the individual also, means Rp value is less than R1, Rp value less than R2, and Rp value is less than even for R3 also. Individually also, that is less than the each separate resistance, that is. Okay, this is about when it is connected in case of parallel connection there. For suppose if you are not using R1, R2, R3 with the three different resistance, if you want to use all three the same resistance there, means for example, as we got in case of the series connection RS, it is we got, if three resistance if you are using, we got R1 plus R2 plus R3, that is. Then if you are taking R1, R2, R3 are same, then it becomes RS is equal to R1, R2, R3, R plus R, it becomes 3R. Like this, if you are using N, then R1 plus R2 plus up to N if you are taking, then it becomes RS is equal to NR. That is of NR, that is. Okay, like this if you are taking up to N or N, then the number of resistance becomes Rn, that is. If R1 equal to R2 equal to R3 there. Okay, and in the same way if you are taking for the case of parallel connection there, then in this case, now if you are taking R1 is equal to R2 equal to R3 equal to and so on, Rn equal to R, then we have 1 by Rp is equal to 1 by R1 plus 1 by R2 plus and so on up to 1 by Rn. As it is of all N only we are taking, then 1 by Rp it becomes N by R. Then the resistance of the parallel circuit Rp becomes R by N, that is. Like this. And if it is of resistance series, if you are taking, Rs is equal to N into R. This is the formula. When if you are taking the resistance always same, that is. Now we will see how to apply this parallel series and this series connection in case of numerical problems. Okay, as we got that resistance whenever it is connected in series, then we are getting the final value R1 plus R2 plus R3 and so on Rn. Whereas if it is parallel connection, if you are taking, we got that is of reciprocals we are getting 1 by Rp is equal to R1 by R1, 1 by R2, 1 by R3 and so on 1 by Rn, that is. Then in this case, now we are taking an example with a simple circuit, so that we are taking with two resistance here, of which one is having 10 ohms resistance and another one with less, which is of 5 ohms resistance then. Then if you are connecting that to a battery there, okay, so that the voltage of that battery we are taking, let us suppose that is of 30 volts battery if you are taking, okay, 30 volts is the battery there. Then for this circuit, now here as the resistance is more here, the potential drop is different and here the potential drop is different, V1 and V2, that is. And we know that the equivalent resistance becomes, in case of series, which is R1 plus R2, whereas R1 is 10 ohms, whereas R2 is 5 ohms, that is. Then total it becomes 15 ohms is the resistance offered in this case, that final resistance there. Then we can take that as of which Rs is equal to 15 ohms. Then the total current as V is equal to IR, as here the equivalent resistance is IRS. Then voltage given there is the 30 volts and current we don't know, and RS value is, let us suppose given is 15 we got. Then I is equal to 30 by 15, which gives you 2 amperes current there. So the current we are getting there is 2 amperes. Then how much is the value of V1 and V2 is, we know that as V1 case, V1 is equal to I1 R1 and V2 is equal to I2 R2 if you take. As this is a series connection, I1 is equal to I2, that is. So, as I1 is equal to I2 equal to I, then V1 is equal to I R1 and V2 is equal to I R2, that is. Then V1 value, that is of we do not know, and I of I is 2 and R1 value we are having, that is of R1 value is 10 ohms, then it is of 10 volts. Then V1 is equal to 20 volts. Whereas V2, if you are taking, V2 is equal to as 2 into here R2 value, that is of 5. So, that is why 5 into 10, 10 volts. So, finally we got V is equal to V1 plus V2, where V is 30, we are getting 20 plus 10, which is of 30, that is. So, mainly what we have to understand from this is the relation to the potential difference to the resistance you are taking there. See here, whenever if you are having the voltage V1 for the case of resistance 10 ohms, when compared to the 5 ohms, 10 ohms is more we have, means the resistance offered in the second case is less when compared to the first case. But if you see the voltage values there, the one which is having more resistance of 10 ohms, for that we are getting the value as 20 volts here, which means that whenever the resistance is more, this battery has to do more work at this resistance. So, that is why here we are getting the voltage is more. So, that is why here V2 value and V1 value if you compare, V2 value is only 10 here, whereas V1 value we got 20 here. So, means the relation between them here actually again same like this. Having more resistance, more voltage is required. Having less resistance is what? Less voltage is what? Required. Depending on the resistance, there is a potential drop is getting in case of this series connection. Like this we can solve the problems if the given one is in the resistance is in the series there. And the same thing even you can apply even for the case of parallel connection also. For example, in case of parallel connection, if you take, let us say in case of parallel connection, now we are taking the resistance 1 and 2 and now we are taking the battery. Let us suppose it is of 10 volts battery we are using, and let us suppose here 2 ohms is the first resistance, 3 ohms is the second resistance, like this. Then if it is of 2 ohms and 3 ohms here, the final resistance here, equivalent resistance 1 by Rp is equal to 1 by R1 plus 1 by R2, that is. Then 1 by Rp, the reciprocal of the resistance in the parallel connection there is 1 by 2 plus 1 by 3, that is. So, 1 by 2 plus 1 by 3, which is of LCM is 6 and 3 plus 2, that is, which is 1 by Rp is equal to 5 by 6. Then resistance offered here, it is of 6 by 5 ohms, that is. Another important thing, if you observe, 6 by 5 which is 1.2, that is, okay, of which we got Rp value 1.2 ohms. If you observe here, resistance for the first case which is of 2 ohms, resistance for the second case which is of 3 ohms, these two individual resistance also if you see, this Rp value is less than that one, of which as we seen in the before the parallel connection there. This is of 1.2 and this is 2 ohms and 3 ohms, that is. Now, if you find the total current passing through the resistance, as it is of V is equal to IR, then I is equal to V by R, of which the voltage here given as 10 by, we got the resistance as 6 by 5, then it becomes 10 by 6 into 5, that is, which is 50 by 6. This is the I value. Then if it is the current here 50 by 6, which is of 25 by 3 amperes, which is around 38.33 amperes, that is. This is the total current here. But what is the current passing through 2 amperes? What is the current passing through 3 amperes? If you want to find that separate, we know that as V is equal to IR, V1 equal to I1 R1, and again V1 is equal to V2 equal to V, that is. So, that is why that voltage also remains as 10 and I1 we do not know, and R1 value that is of 2 ohms there, then I1 becomes 5, and whereas I2 if you are taking, that is of V2 is equal to I2 R2, then V2 is equal to 10 again, I2 we are finding and its resistance is of 3, then I2 becomes 10 by 3 which is of 3.33 amperes that is. Then finally we got the total current I, 5 plus 3.33 which is again 8.33 amperes. Like this. So, that current of 8.33 amperes is divided as with 2 amperes, 2 ohms there, I1 which is equal to 5 amperes and I2 there which is of 3 ohms resistance is taking 3.33 amperes there. The important thing here we have to observe is the resistance of the second one is more. So, that is why the current for that is less, which is only 3.33 only present. Whereas, in case of the resistance less case which is of 2 ohms, the current passing through that is 5 amperes we are having that. So, means depending on the resistance again, now this is for the case of series we seen, where the relation is like this. Now, we are coming to the case of parallel connection. So, that in case of parallel connection, it is a bit different one we got, of which from the parallel connection, we can conclude that if you are taking R2 value is more and R1 value is less again, R2 greater than R1 like this. Then as R2 is more, then it's the current passing through that I2 is less, I2, I1. Then I2 value is only 3.33 only present. Whereas I1 value it is of 5 amperes we have. So, means here I1 is more and I2 is less. So, having more resistance there, then the current passing through that is less. We are having less resistance is there, the current passing through that is more. Having a less resistance, more current we are having like this. This is in case of parallel connection we see. Now, we already seen how the circuit, how to solve the numericals if you are taking a parallel circuit and how to solve that if you are taking a series circuit. Now, we are merging both. We are taking a series connection one as well as a parallel connection one. For example, like this. With the resistance which is in series with 2 more resistance there, like this. So, let it be this is R1, R2, R3 and now this one again connected to the battery, okay, like this R1, R2, R3. R2, R3 these two are in series, these two are in parallel, whereas R1 it is in series with the R2 and R3 that is, okay. So, like this. Now, let us suppose here if you are taking this value R1 value if you are taking and I want to find the equivalent resistance between A and B. So, that R1 value is 2 ohms, R2 value let it be 3 ohms and this one value let it be that is of 4 ohms, 2, 3 and 4 that is. Then at first if you see that R2 and R3 as they are in parallel, now we can change the connection as like this. Between A and B where R1 is present which is of 2 ohms now and 3 ohms and 4 ohms as these two are in a parallel connection we can write that as 1, okay, and after that again we are having that battery is there and this value now we are finding, let it be that is Rp when they are in parallel. Then 1 by Rp is equal to, we know that 1 by R1 plus 1 by R2 that is, okay. Then 1 by Rp where Rp is equal to the resistance when connected in parallel by 1 by 3 plus 1 by 4 that is. Then if you take LCM here 3 and 4 12 and which 4 plus 3 that is 1 by Rp, then Rp becomes 12 by 7 that is of 12 by 7 ohms. Now, we got the Rp value which is 12 by 7 ohms that is, okay. Now, as these two are connected, now it is in series, then we have to add both that because Rs is equal to R1 plus R2 plus R3. Now, this circuit again we can change that as like this between A to B. Now which are in series? RS and the battery is there. Now this is AB. Okay, then simply add both the resistance, that is our final resistance, that is of which RS is equal to 2 plus 12 by 7, that is. If you take LCM, 14 plus 12 by 7, which is 28 by 7. Okay, sorry, 26 by 7, that is. 26 by 7, that is. These much ohms. Okay, so this is the final resistance we got. If you are taking both, two are in a parallel, and that parallel connection you can take that with a series. Okay, and if you see the value there, 26 by 7, here the reciprocal when you are taking for the case of parallel connection, these two resistance 12 by 7, which is 1 point something, is less than both 3 and 4. And not only that, if you are taking the series one which is added, then 2 plus we have to take. Okay, more value we are getting. 26 by 7 means we are getting here 7 threes and 0.7, approximately 3.7, which is more than 2 ohms we are getting that. Okay, so that's why in case of series connection, here the resistance value is increasing, whereas in case of parallel connection the resistance value is decreasing, that is.